Hi everyone, in this lecture I am going to discuss about spectral shifts, that is changing the peak. We all know the peak, that is the spectrum that we obtained from UV visible spectrophotometry is a fingerprint for each and every compound, but there may be changes that will occur when you introduce some changes to our compounds, or if you change your solvent, many differences may occur. So spectral shift are one of those effect. The spectral shifts can be classified as bathochromic shift, hypsochromic shift, hyperchromic shift and hypochromic shift. A bathochromic shift, often called as a red shift, occurs when maximum absorption wavelength, that is lambda max, moves to a longer wavelength, indicating a decrease in energy required for electronic transition. Bathochromic shift is otherwise called as a red shift, occurs when maximum absorption of wavelength, that is lambda max, moves to a longer wavelength, indicating a decrease in the energy required for electronic transition. So the bathochromic shift is otherwise called as a red shift, and here the lambda max of our compound will shift towards a longer wavelength. So we all know, we have already discussed about this in oxochromes. So if we add oxochromes, or if we make or convert our compound into a conjugated one, or if we add any amino group or electron withdrawing groups, then we have made some changes to our compound, and the lambda max of that particular compound will shift towards a longer one. So that is called as bathochromic shift. Then a hypsochromic shift or blue shift indicates a shift of lambda max to a shorter wavelength, meaning a higher energy transition. As you can see, the hypsochromic shift is otherwise called as blue shift. It is the exact opposite of bathochromic shift. In bathochromic shift, we need our compound to be a conjugated one. It should consist of a double bond or triple bond, and it also will consist of substituent groups such as amino group or halogen groups, or any other electron withdrawing or donating groups. Here in hypsochromic shift, we need our compound to be a saturated one. So and also our compounds will not have any substitution groups. So either by dealkylation or by doing hydrogenation reactions, that is desaturation reactions, then our compound can be converted into a one which can give rise to a hypsochromic shift, that is blue shift. So your lambda max will now hyperchromic effect. Hyperchromic effect is observed when the absorbance intensity increases, and while a hypochromic effect indicates a decrease in intensity. So this depends on the absorbance of our sample. If our absorbance increases but the lambda max will be similar, only the absorbance will increase. It depends mostly on the solvent. And the hyperchromic shift is indicates the decrease in absorbance intensity. Bathochromic shift. A bathochromic shift signifies a movement of the absorption maximum towards a longer wavelength, implying a reduction in the energy gap between ground state and the excited state of a molecule. Several factors can induce this shift. Firstly, increased conjugation within a molecule plays a significant role, extending the pi electron system as seen from butadiene to hexatriene. For butadiene, the lambda max is 217 nanometer, and for hexatriene it is 258 nanometer. The difference between these two is the number of carbon atom has increased and the diene has become triene. So the conjugation or the double bond or triple bond unsaturation has increased, leads to delocalization and a small energy difference. Secondly, the interaction with electron donating oxochromes can stabilize the excited state and thereby lowering the energy required for transition. Lastly, the solvent polarity can also cause a red shift, particularly for pi to pi star transitions, where more polar solvents often stabilize the more polar pi star excited state to a greater extent than the ground state, leading to the diminished energy gap. So what is happening if we consider our compound to have all these characteristics, then which means our compound is going to be stable in the excited state for a longer duration of time, then there is a possibility that it can observe the wavelengths that are longer. than the usual normal ones. So when we induce these kind of changes to our compounds, then definitely they are going to absorb the longer wavelengths. The increased conjugation, expanding the pi electron system, lowers the transition energy, and oxochrome interaction, electron donating group stabilizes the excited states, and solvent polarity. Polar solvents stabilize the excited states, more reducing the energy gaps. Then hypsochromic shift and solvent effect. A hypsochromic shift where lambda max moves towards a shorter wavelength indicates the increase in the energy required for electronic transition. One primary cause is decreased conjugation. For instance, the protonation of aniline breaks the conjugation of amino group within the benzene ring, shifting the lambda max from 280 to 250 nanometer.